Thanks a lot for coming back. It's nice to see everybody again, a lot of familiar faces. Tonight is the second in the series. As Gus said, this is meant to be a hands-on workshop for a general audience, okay? So we're not going to go too deep, except for tonight, we're going to talk about advanced topics a little bit at the beginning before we go into the hands-on section. Just kind of stuff that I thought you should all be aware of, because you're all engineers, and it's just something that if you hear it now, maybe it'll make it easier for you when you step out and try to do a board on your own. So we are going to do that talk and then go into the actual process of working on layout in KiCad tonight. So last time I left you all with some homework. So install KiCad if you haven't already done it. Go through the KiCad guide. Think about what you actually want to design, and then go out and buy an Arduino because it's a toy that's fun to play with if you don't have one already. And then the key thing that I left you with is that I don't really trust these components that come out of the library. So I said, could you guys go and check this Arduino R3 that comes from KiCad, and does it look correct? So I gave that as homework. We're going to talk about that a little bit here at the beginning of the talk. But before I do that, I just wanted to open up the floor to see if anybody had any questions over material from the last lecture or just anything else. All right, so I mentioned the last time, I'm scared to death of these parts that come out of the library. I have to check them before I put them on the board because the board will be wrong if that part is wrong, and it'll be a pain in the neck. I have to redesign the board, respin it. It will cause me a delay, cost me money. So when I first played with this Arduino R3 and KiCad, I was like, okay, where do I get mechanical information on the Arduino? You would think that this is easy, okay? But I spent 10 minutes and I couldn't find a good mechanical drawing on the Arduino website, which is bizarre. So I actually had to find them at other, websites, and I found this thing here on the right-hand side after a quick search. So, okay, is it right or wrong? I don't know. So at that time, it was at my house drinking coffee. I did not have my caliper, so I had to resort to using tape measure. But I did some mechanical analysis, which, as I talked last time, designing a PCB is a marriage of mechanical and electrical engineering. So, I had to break out this device to see sort of the pin placement and the pin sizing on the actual Arduino. And the result was that thing that I found was wrong. So this document on the guy's website was just wrong, okay? So that made me go looking for another option, and I did finally come across something here on the right that actually agreed with the physical Arduino, okay? So now I know I have dimensions that agree that I can follow. The question is the component in the KiCad library correct? So did anybody do that exercise? Nobody did it. So the answer is it's kind of correct, actually. So you can really use it as is. You just have to make a few modifications. And we're going to do that when I go through the tutorial later where it's hands-on and you guys will be playing with KiCad. I'll kind of walk you through what I had to do to make it usable for my board that I designed. Okay, so before we get into the actual KiCad stuff, as I mentioned, there are some advanced topics that I just wanted to introduce, which are a big part of knowing how to design PCBs. The first thing I'd like to talk about are decoupling capacitors, okay? So you could look at a schematic of a board. So this is a board from a place called Digilent. They make FPGA dev boards for people to sort of play with, like a hobbyist type FPGA board. So on that schematic, you see a bunch of capacitors connected between power and ground, but they're not doing anything else. So the question is, why are these here? Does anybody know why somebody would put those capacitors in that schematic? Go for it. So exactly what the gentleman said. It's used to sort of even out the noise, but more to really stabilize the voltage level across the board, especially for the ICs on the board. So that's one of the key issues. So what do the capacitors do? They're little energy reservoirs. So if there's a spike in the chip that needs current, that capacitor, you place it very close to the chip, and it will supply the current that chip needs. I'll talk a little bit more here. But if you don't have a capacitor close to this chip, on the board, there's a long interconnect network that is inductive, that is capacitive. And that network feeding to the chip will introduce ringing and all sorts of unwanted behavior on the supply. So if you place a capacitor close to that pin on the chip, it will smooth the supply for you and hopefully make the operation of the chip better. Now, just a key point, I kind of said it during the talk here, but when you place these capacitors physically in the design, you always want to place them as close to the IC that you're trying to protect, because you want to minimize that length of the parasitic connection from the power supply to the pin on the chip. Okay, so how do I know what capacitor to use? That starts with this rule of thumb, which you can find in a lot of locations. But basically, if you know the rise time, the fastest rise time on your board for a given chip, you know the voltage of that chip, and you know the amount of current that chip is consuming, you can just roughly calculate how much capacitance you need in order to smooth out the supply, okay? Now, this is only valid if your bandwidth is less than the self-resonant frequency of these decoupling caps. So I put this question mark here. What does that mean? So does anybody know what self-resonant frequency means related to decoupling capacitors? Go for it.
So a capacitor has parasitic inductance and parasitic resistance, but inductance is probably going to matter more here. And that creates an LC network that can resonate at a certain frequency. And so even though it's really small and that frequency is generally very high, if you're running super high frequency, that can cause a resonance, which has the opposite of the intended effect that you want. So instead of smoothing it out, it starts bringing and oscillating and pushing that noise back onto the line you're trying to feed the chip.
Exactly. Yeah. Yeah. So I'm not going to repeat the answer, but the gentleman in the audience got it 100% correct. But I'm going to talk about on the next slide that. So one of the key things you have to do, you have to consider the signal bandwidth that you're working with, and that signal bandwidth is of roughly 0.35 of the signal rise fall time. Okay, so as the gentleman answered, yep.
Do you have any suggestions for a typical capacitor value or type, or will we get to that in a minute?
Well, I'll kind of talk about it. So in terms of value, we kind of touched on the rule of thumb. I'll talk about it on this slide. But in terms of particular capacitor type, absolutely. There are capacitors that are designed for high-frequency applications or low-frequency applications. So, you can pick a capacitor that works better than others for this application, okay? The nice thing about decoupling caps is usually you don't really care about the actual absolute value. So you can get sort of a cheaper cap that has a wide error on it. So you could get a 10% rather than a 1% because you don't really care that much. You're just you basically over-design. When you're putting decaps on, you don't really go for the minimum. You kind of always cover yourself a little bit greater. So here on this slide on the top left is the model that one of the folks in the audience mentioned, that a capacitor is not just a capacitor in real life. It actually is comprised of parasitic components. So it's got a series resistance, it's got a series inductance, and then you have the capacitor value itself. And then there's a parallel resistance with that capacitor too. So it's not, it's not just a cap. So what does that do? Over frequency, the capacitor value is not the fixed value that you thought you had. It actually changes over frequency. And that change is a function of the value itself. And what you can see from the trend here is that the larger the capacitor value, the lower the self-resonant frequency is, okay? So if you want to filter a high frequency, you can't choose this large cap value because the high frequency is over here. What happens on this transfer curve is that the capacitor actually becomes more inductive once you cross that self-resonant frequency. So you don't even have a capacitor anymore. You've got an inductor, which is a bad thing, okay? So, you know, there's a lot of stuff out there that you can read about it, but it's just, you know, I kind of wanted to point it out to you guys because, you know, it's you can hear it from me talk about it for 5 minutes versus Googling stuff for hours. All right, so any questions on decoupling caps? Okay. The next thing on the advanced topic are ground planes. So oftentimes you'll design a PCB. It's got traces everywhere, and then you'll see underneath is a solid plane, and you may wonder why is that the case. So ground planes are actually useful for many things. It's a large area of copper. So one thing that's very simple that makes it useful is that it's easy to make a lot of connections. So on this picture over here, you can see that resistor is connected to ground. This connector is this side of the resistor is connected to ground, and that connector is also connected to ground. So if you had 1,000 connections to ground and you have a ground plane, you don't actually have to make them. The tool will make that connection. Before I go beyond that, if you look at the way that connection is made, does anybody want to tell me why it might look like that? Go for it.
I mean, I can describe that that's a spurred connection or spoke connection.
Sure, it is a spoke connection, yes.
I would have trouble telling you why.
Anybody else? Okay, so this structure is called a thermal relief. So why would you do that? If you're the person soldering that solder joint and you're trying to solder a big piece of copper, it's going to take a long time to heat that piece of copper up enough for the solder to melt. So when you have these thermal reliefs, it actually increases the thermal resistance so that you can actually get that solder joint hot and make a solder joint easily, okay? What do you lose with that? Well, you lose the purity of the connection from that node to ground. So it now it has more resistance, but you're able to solder it. So what else does the ground plane help you with? It gives you, if you do the ground plane right, it gives you these really low inductance return paths. So as you all know, if you're sourcing a signal from here to a load, that return current has to flow back to the source. If you have a solid piece of copper, that current can just go exactly the way it wants to get back to where it wants to and be, you know, and encounter the least obstacles that it can. If that current had to flow all over the place to return back, you would end up having a slower signal. So ground planes help with that. Another thing is for EMI. So that ground plane is a shield. If you had something underneath this board that you didn't want to couple noise to, you have that ground plane there that will block any kind of EM radiation. Another thing that I'm going to talk about in the next slide is impedance control. So I'm not going to touch on it here. And finally, you know, you don't just have to have ground planes. You can also make power planes that can serve some of the same functions, but they're distributing power instead of ground. All right, so, you know, last week a couple of people were talking about transmission lines. So if you're doing any kind of high-speed design on a printed circuit board, you're going to need to know how to make a transmission line. And basically what they are waveguides on a PCB, okay? So it's a very in-depth topic. Dominic in the room knows all about it. He's done it on ICs and on boards many times. Also, Gary is not here. He's done it too. But it is an art form in a way, okay? So what do they allow you to do? They primarily allow you to do impedance matching, okay? So in order to do max power transfer, the source impedance has to match the load impedance. By designing these traces correctly on your board, you can do that at RF, okay? So I'm not really going to go into detail there, but just kind of wanted to introduce this to you all. So why are transmission lines important? As I talked, for max power transfer, you have to match the source impedance with the load impedance. And you typically would do that, let's say, if you had a 50 ohm environment, you would have a 50 ohm transmission line and a 50 ohm load wherever your signal was going. So ideally, that voltage on the line, if your transmission line was lossless, would just be a square wave if you had that perfect match. But in real life, the actual transmission media on a board is not lossless, it's lossy. So you can see what you end up with, something that has actually a slower rise time than what you want. And that's due to the material properties of the copper and of the dielectric material that's used to make the board. Okay? That's step one. Step two is, what if you actually have a mismatch? So you try to get 50 ohms, and you tried to get 50 ohms here, but you miss by a little bit. Well, what happens is then you get reflections on your transmission line. And at the end of the day, it's going to show up as ringing like this if you actually measure the board. So carefully, knowing about this effect, knowing how to design transmission lines can save you if you're actually trying to do a high-speed printed circuit board. So transmission lines, they come in a lot of flavors. You can, there are a lot of geometries you can do, and this is just an example. The most common here is on the top left. It's a microstrip. So it's simply a trace over a ground plane. You have other types. You can bury the transmission line in between a ground plane. If you had a diff pair, you might use structures like this or like this. But there are many, many, many shapes and forms of transmission lines that you can make. So how do you, as a designer, actually do this? Like, you have these shapes, you have the material properties, you know what impedance you want. How do you figure it out? Well, it's a pretty well-known art to be able to calculate how these are built on PCBs. And I just threw this up here. If you look them up, you can find equations for microstrips. So you could then calculate, if I wanted a 50 ohm line, what would I need to do? How wide would I make my trace? How thick does the dielectric need to be? How thick is the copper? All of that stuff plays into determining the impedance of that transmission line. All right. So any questions about transmission lines before we go to the next? Go ahead.
In these equations, is T the temperature, like the highest temperature it's going to reach? What's T?
T is the thickness of the signal conductor. Yeah. And we talked last time, how do people specify thickness? Like, what word do we use to describe that? Does anybody remember? That's it. So we have the winner. They said ounces. That was correct. Okay. Go for it. Yeah, sorry. So the question was, does KiCad offer any tools to help with this? The answer is yes. I will say that in that regard, I touted KiCad's capabilities. This is one of the features that, is maybe not as advanced as, some of the other tools that are available. Okay, so I think this is kind of the final thing before we go into the actual work together. IPC classes, okay? So generally, boards are separated into 3 categories: IPC class 1, 2, and 3. What does that mean? Well, in a nutshell, IPC class 1 is the cheapest board you can buy. IPC class 3 is a more expensive board. Why is that? Each of these classes are constraints on the printed circuit board manufacturer, how they control the manufacturer of the board to make sure that tolerances are met. So in a class 1 board, the manufacturer has a much easier job in the case of a class 3 board. So I have a slide next that sort of highlights that and explains that. But can anybody tell me, why would I want a board that has tighter manufacturing tolerances? Go for it.
Extreme environment, so there's a higher requirement for it to be at spec.
Okay, so the answer was that it would be good for a more extreme environment, so you can predict that it's going to work the way you thought it was going to work. I think that's a reasonable response. Does anybody else have, go for it.
Goes into space, you can't get it back, so you better make sure it works.
Okay, so this one was, if it goes into space, you can't get it back, so you better make sure it works. The answer is yes. You're right. Anything else? Anybody else? We just talked about it. We just talked about this. So, how about this? All these widths, traces, thickness, that matters for the performance of these guys. So you might have to pay a little bit more to get these guys to work better. Okay. Yeah, so this is like a super cute picture, I think, of if you're a printed circuit board manufacturer and you want to meet these IPC classes, what do you have to do, okay? What you're seeing here on the left is a cross-section of a printed circuit board, and this is a via. So we talked about what vias are last time. It's a hole drilled through the board that connects the top layer through layers in the board. And then there are all these numbers kind of pointing to features, right? Each of these features are things that the printed circuit board house has to guarantee are going to meet a certain level in order to meet IPC class 1, 2, or 3, okay? So just a via has 42 items that the printed circuit board company has to guarantee. So what do you do as a consumer? When you buy an IPC class 3 board, they send you something that's called a test coupon, okay? And that is a cross-section. They would take the board that they made for you, and then they would send you a cross-section of one of them, meaning a physical one. They would take the board, cut it in half, put it in epoxy, polish it, and send it to you so you could see for yourself and measure the vias that they actually fabricated, that they came out to be the spec that you paid for, okay? So, I've actually had projects where we had IPC class 3, something went wrong, we had to go in and look at what they did with the vias, and they screwed them up. So it was an issue where we had the thermal cycling, and vias were failing. We couldn't have vias fail because where we're going to take this thing, it couldn't be touched for 10 years. So we had to ensure that it was good. So anyway, I just thought this is kind of a cool thing that we maybe would never think about. All right, so any questions at this point before we turn on KiCad? Go for it.
What's a use case where you're not allowed to touch anything on a board for 10 years?
Sure. So the question was, what is a use case where you wouldn't be able to touch a board for 10 years? So we had one of the audience members mention space, like Voyager, for example. They launched it in 1970, whatever. It's still flying, and it's the farthest thing it's the farthest thing human beings have ever sent out from the Earth, right? It still works. Okay, it's been there for 40 years. The stuff I worked on was physics experiments, high-energy physics experiments, that once you turn them on, they get radioactive, and you have to wait for a long time for them to cool down enough for humans to go inside and be able to operate on stuff. So the on and off, takes years. So, any other questions? Okay. All right. So now what we're going to do is drive KiCad. Okay. I have a cheat sheet of the things I'm going to go through. And I don't know, again, nobody has any questions. We all are good at KiCad. There's nobody played with this and got stuck? No? Okay. All right. So just to show you this, when I made these slides for another avenue, and I kind of repurposed them for this talk. But I made this board right here. So it's exactly what we're talking about. It's an Arduino shield, and it ended up looking like this. And so that's we're going to kind of use that today as I go through the example. Okay, so right now, all I'm doing is opening a project. So I made a copy of that project that I just showed you. If I open up the schematic, we will see it here. It's got more stuff on it than last week, but it has the Arduino that we talked about. It has LEDs that we talked about. It has resistors. It's got a few more things. Okay, but what I made was just a free space optical link. Like I had a transmitter and a receiver, and I took two of these and I talked to each other, like, something basic like that. So that's the schematic. And we're really not going to focus on this because I considered last week's lecture, as much as I'm going to cover schematic-wise. So if you guys have schematic questions, ask them, that's fine, but I'm not really going to do much here on that. Let's see. So PCB editor is here. So what I wanted to do, hang on a second, I'm going to start over. Give me this. So I had a backup of the original PCB that I kind of played with when I was getting ready for this. Okay, so here it is. Okay, so this is the final design. I showed you guys a picture just now. This is what it looks like. So it's kind of annoying, I think, that KiCad puts this sheet on there. So how do you turn that off? I wish Gary was here. Is Gary here? Gary's not here. It's in objects, I think. Drawing sheet is gone. Okay, so drawing sheet is gone. The next thing I want to do is just kind of show you guys what this board consisted of when I finished it, right? What I'm clicking over here is the display window, which is very important for the PCB designer to be able to turn things on and off to see what's actually going on, okay? So I hated that border boundary thing, so I just got rid of it. It's not deleted, it's just not shown anymore. Let's see over here. The layer menu is, if you're actually doing an active design, you're going to be working over here quite a bit. But I can kind of go through here and turn off layers until you really don't see anything. Okay. What I care about is the copper. So FCU is the front copper, that's the top copper. BCU is the back copper, so that's the bottom. This is a 2-layer board. And this looks like a sheet of metal, right? Well, if we zoom in, let's see if I can find one. I don't know if I have thermal reliefs on this board or not. But you can see these are ground vias that are just shorted to ground. There's no opening. On these guys, there's a relief so that they're not shorted together.
We have a question online.
Let's have that.
So the question is, how are you zooming in and out with it still remaining in the center?
That is a great question. How do you zoom in and out with it remaining in the center? If you recall, I said last week that in order to use KiCad, you have to have a mouse, at least for me. The way the zoom works is that you just, wherever your mouse is, if you scroll with the scroll wheel, it zooms to that point. So if I wanted to zoom to this guy here, I just scroll over and then middle scroll wheel to get there, okay? All right. So that's the board. I just kind of wanted to quickly show it. But what am I going to do now? I'm going to delete everything and start over because we're going to talk about layout tonight. So I do a Control A. I'm going to put on the back copper. And one of the key things that I want to talk about is this selection filter over here. The selection filter is very important because there could be cases that, what if, for example, I didn't want to delete vias? I could deselect everything, or let's say I only wanted to delete vias. If I have vias selected, and then I do a Control A, it's kind of hard to see from this view, but the vias are selected. If I delete them, they go away. And I have, in that command, by only selecting vias, I've deleted all the vias. There could be a case where you would want to do that. Traces are the same. They call them tracks in KiCad, so I could do the same thing. I can delete all the traces. Boom, done. But I'm just going to delete everything now. So I'm going to... there's another feature that is kind of nice called locking. So this feature allows you to, if there's a component in a place that you don't want to move because it's mechanically important, you can click on that component and lock it in place. And then no matter what edit you do, it cannot be changed. So you can, lock things in and out, and that's pretty convenient. But I don't really care, so I'm going to delete this. So it's asking me, oh my God, you have locked stuff. I don't care. I'm going to override, and I'm going to delete the locked stuff. Okay, so the board is gone. So we're going to be starting over. So before we do that, do we have any questions at this point? No? Okay. So the first thing I want to talk about are the grids. I touched on this a little bit. One of my favorite features about KiCad is the fact that you can bounce between units on the fly really trivially by clicking on these buttons on the left where it says inches, millimeters, and mils. The other thing that's nice is that you can change the grid really easily on this drop-down menu right here. So if you click that button, there's a long list of grid values that you can select from. And you can even type in your own if you wish. So at this point, I would ask, does anybody know why the grid is important, or why is it useful? Go ahead. Right. So that was a good answer. The answer was that you can use it to force things to be placed on a certain pitch. If you want it to be precise, you could use this method to place things on a precise grid, which is correct. Anybody else? Sure. Okay. So the answer was you could use the grid if you had a design for manufacturability concern, sort of how close components can be placed. You could use that grid when you're placing components to keep the devices separated enough. And that's a great answer. Sure, you could do that. Okay, so we've got the grid discussion out of the way. What I'm going to do now is place the parts from the board. And if we remember from last time, that's simply clicking this button right here, Update PCB. So I'm going to do that. It says the schematic is open. I don't really care. It's thinking. Okay. And you can see, unlike last time when we did this the first time, we have no warnings, no errors. So we're ready to update the board. I would click Update PCB. And like last time, all the components are in my hand, and I can drop them wherever I want. So I'll do that. And I'm going to turn some of these layers back on so we can see stuff. Okay. All right, so now we have all the components from the PCB that I showed you guys, the schematic. All right, so we see these colorful sort of lines that are strings connecting things from here to here, here to here, here to here. Does anybody know what those are? Go for it. Yes, so the answer is from the audience that this is a rat's nest. That's exactly correct. What is a rat nest used for? It's to tell the user what has to hook up to what. Okay, so I'll kind of, as we do this, we'll use that rat nest to our advantage. So we talked about the Arduino and how we need to do a little bit of something to make it useful. I'm going to do that right now. I have to turn on some stuff. I don't know why. Oh, I know why. Properties. Yeah. So yeah, I think I have, so the version I have here is already edited. But if you recall from the slides, I'll just show you rather than do it again. But from the slides, the Arduino had all this, like it had the actual connectors. It just had a mechanical sort of drawing of the connectors, but it also had an outline that is larger than what I actually intended to put down, right? If we go here, if the board was that large, it would hit the connectors on the Arduino. So what I had to do was go in, delete that boundary so that it wasn't there in the board itself, so that I could use it for my purpose, okay? All right. So let's hop back over here. And we talked about in last lecture, sort of the most important thing in PCB design from my point of view, like to make your life the easiest, is actually getting the placement of the components right before you do any routing at all. So you put the Arduino where you want, you put the chips where you want, you put the decaps as close as you can to the chips so that you have good power supply distribution on your board. So the component placement is critical, okay? For the sake of time, I can't do the component placement here because it would probably take me a couple hours to get it right. So, but just for here, I'm going to kind of play around and just talk through what I'm thinking as I do that process. So what I remember is that, so the R key is rotate. So I'm just hitting R after I've selected the Arduino, and it's rotating. And I know I need to flip this guy to the backside as well. That's another thing, because I wanted to plug this down onto the Arduino. So I can flip the side of the board that component is placed on by pressing this button here, change side flip, and you'll see the connector go upside down. Okay. And in fact, I was wrong about this. So that outline is still here. And I'm not sure why that's the case. It was, there's something with my view that I can't see. I couldn't see it when it was on the other side of the board. So, but let's actually do the edit now then. So you can see it has this annoying outline that I didn't like. How I fix that, right click, open in footprint editor. So we talked about the KiCad project last week, where we have schematic, PCB, but we have the symbol editor and we have the footprint editor. What I'm going to use now is the footprint editor to modify the footprint of the Arduino, and it's simply to remove this outline. So I'm going to go through that footprint editor, and this guy will fire up, and I'm just going to get rid of this because it's annoying. Let's see. So all I'm doing is highlighting and deleting. And there are multiple layers that make up this outline. If you hover over the shape, at the bottom of the screen here, you'll see what layer this corresponds to. So if I click, I've highlighted this guy. Where is that? I don't see it now. It should tell you somewhere what that is. But all right. So another thing that I had to do was keep one layer, which is FFab. So FFab tells KiCad that this is a part altogether. So I'm going to draw back the FFab layer, which is somewhere here. So to draw a rectangle, you click on this guy. You click on FFab in the right-hand side, and you can see there's an arrow showing you that that is the active layer. And then I can just draw, then I can just draw a rectangle that encompasses the Arduino. This is probably good enough that if I made the board and plugged it in, it wouldn't collide with anything, okay? All right, so I've done that. All you do is save this guy and close it. And then when you go back, the outline is no longer there. Okay, I'm going to pause and ask if there are any questions at this point.
So what you just did just declares the outline of the part itself, but you
Right.
haven't established the board size yet.
That's on the list. I'm going to do that. So the question was, why did you bother modifying the outline of the part when you haven't defined the board size yet? And that's a good point. So if I hadn't modified the outline of this, it would be bigger than the board. So I would have the board outline, but then I have this crap hanging off. So that's why I got rid of it, so that it's going to be all inside of the board. Does that make sense?
Yes, you can still design it so that there's some crap hanging off, right?
Yes.
It just won't have like that silk screen on the board.
So
Annoying to look at.
well, so let's say, for example, so the answer was, you can still design it so that there's stuff hanging off of the board edge. Yes and no. If you draw a piece of copper that's outside of the board edge, the PCB house is going to say you have copper outside of your board. That's a problem. Or if you have solder mask outside of the board, if you had silkscreen out of the board, that would break a DRC rule. So that's why you would want to keep things contained. All right. So get back on track. So one of the cool things about KiCad is that it has a really easy to use, user-friendly 3D viewer feature. So we're going to check that out now. I'm going to go over here, view 3D viewer. Okay, it takes a second, and there we go. We have our board. We have our parts. Our parts are not on the board, as we know. But this, as you can imagine, could be useful to you as a PCB designer. All right. So now we're going to do the thing that one of the audience members mentioned. We need a board outline. We need to define what is our place that we can play within, our sandbox. So I'm going to do that. And the layer that's used in KiCad to define the board outline is called edge cuts. So I'm clicking on edge cuts over here in the layer window, and I'm going to draw a rectangle. Oh, I already have it. Fascinating. I have an old edge cuts down here. So who knows about KiCad? Sam knows about it. Flip does. Why are my things hiding until I turn them on?
What about at the bottom there's like a
Presets.
presets?
Doesn't it was on like dash dash dash. So I just do all layers?
Yeah, just turn everything back on.
Oh, lovely. Now I'm going to get rid of this guy. So I did not come here claiming to be an expert on KiCad, although I can kind of use it. I've designed hundreds of boards in my life over various tools. I just, this is not my day job. Let's put it that way.
What's your design tool of choice?
For
yourself, for boards that you work on it.
Oh, right now I love this thing. Yeah, it's just like the point is I will, if I design a board like the week after, I know how to do this thing, but then I just forget because other things take over my life. So, okay. All right. So you guys saved me. Thank you. I want to turn off this gosh darn drawing sheet because it's annoying. It's gone. And I'm going to draw the board outline, as I mentioned. So I'm going to hop back over here. Flip, thank you for the help. Do we have any questions at this stage? Are people doing anything in KiCad right now, actively? Okay. I didn't come here prepared to teach you how to do that, because this is actually hard. Like this actually, I had to Google stuff, and maybe took me an hour. But then once you get it, it's easy. It's just, again, last week when I talked about KiCad, the beautiful thing about it is that because it's open source, a lot of people use it, a lot of people comment on it, there's a lot of resources online. Not a big deal to do it. And yes, this is the actual official OSU logo that I downloaded from the website so that I wouldn't be sued. And I, streamed it in here. Okay, so let's draw the board outline, finally. Let's see. What did I say? Edge cuts. Here it is. We're on edge cuts. We've got the rectangle tool. I'm going to draw a rectangle, roughly encompassing where the Arduino is. For the sake of this, exercise, we don't have to be exact. But if you were really designing this yourself, you would get the dimensions right. And KiCad has a nice measurement tool, which I can't remember where it is. Inspect measure tool. So you can, check your dimensions if you want. You can also arbitrarily determine the size of the rectangle by clicking on it, doing properties, and typing in coordinates to make it the exact size that you want, which is probably what I would normally do if we weren't in this time crunch just to go through the process today. All right, so I'm going to get rid. I don't want these silk screens anymore. We'll keep this one because it's kind of fun. So I'll put it here. All right. So I already talked about the selection filter. What I'm going to try to do now is place the components. So the key with that is I need to know what the move and the rotate command are. Move is easy. It's just M, I'm pretty sure. Right? So you just, if you hit escape, you stop moving. But if you hover over a part, hit M, it will pick it up. To make this easier, I would normally use the selection filter. I would turn everything off. And what I'm going to do actually is I'm going to lock the Arduino. I think I am. I'm going to lock the Arduino so that it doesn't move. Somewhere is a button to do locking, so you just lock. It's that easy, lock it. It's kind of annoying because it has this purple thing. I don't know if I like that, so I'm going to turn. Do you guys know how to turn off the lock view? Locked item. There, it's gone. So that was easy. Go back to layers and back to the selection filter, and I will just click parts. And now I know all I'm picking up are parts. So if I try to pick up the silk screen, you can see it doesn't let me. But if I go over here, I can pick up this connector, okay? So as a PCB designer, where should I put this guy? How do I know? Does anybody, any answer is good. Go for it.
The place where the rat's nest is the least rat nest. I don't want anything crossing here.
Okay.
Or at least the minimum number of things crossing here.
Okay, so this is a great suggestion by the audience. They said you should arrange it in such a way that there's as little crossover as possible in the rat's nest. I completely agree with that. Why might that not be possible? Go for it.
You turn it one way, it creates a rat's nest one way, and you turn it another way, it just mixes different traces.
Right. So the answer there was you might not get lucky. You might turn it one way, it makes one rat nest bad, but you turn it the other, it makes the other, so you can't win. So that was a great answer. The answer I want to provide is that maybe there's a mechanical reason that the connector has to sit here, this connector has to sit here, and you have no choice. So that's the other reason. All right, so let's kind of do this guy. Okay, so I'm rotating and moving, and wow, look at that. Doesn't that look clean? Like those things are just lined up straight. Isn't that convenient? Why might that be? Would anybody like to guess why it's just straight like that?
Outside of that, you designed it that way.
So the answer from the audience was brilliant. It said, outside of that you designed it that way. Yes, I designed it that way. Let's take a look at the schematic. So here's a cute thing about KiCad is that when you click on a component in the layout, it highlights it in the schematic, which makes it very convenient to figure out what part is what. So I have this connector highlighted, and you can see I just made straight connections, and that's why it looks like that. Okay? So what does that tell you about, schematic entry and PCB design? What it tells you is that if you do a good job in the schematic, it makes your layout easier. So once you learn how to do both things, you'll learn that I should do this in the schematic to make my life easier when I'm doing the layout. Okay? All right. Okay, so that one was easy. We're just going to put it right here where it's supposed to be. Everything else, I really don't care for the sake of tonight. So let's see here. Let's take this guy, just move this pile. So I just made a big selection. I'm going to throw these guys up here, throw these guys over here. Okay. All right, so everything fits. So let's pretend that I'm done, that I did the placement and I'm happy. All right, so let's hop back to the 3D viewer real quick. I just thought this would be a useful point to show something. Click here, 3D viewer. This brings up the PCB, which now almost looks like, a PCB with parts in the right place. You can toggle view of components on and off readily like this, which is kind of nice. The reason I learned this today is because I couldn't figure out how to see the caps, and I had to go talk to Josh. I don't think Josh is here, but he's like, "Oh, you just click that button." I'm like, "Oh, okay." But it's a nice tool, and one thing you can see here is that the Arduino itself doesn't have pins. Where normally, or sorry, not the Arduino itself, but the shield doesn't have pins to plug into the Arduino in the 3D view. That doesn't really matter because I'm going to solder them in anyway. But it's actually pretty easy to add them. And I'll just kind of quickly show you that. I'm not actually going to do it. But if you go back here, let's see. And I'm trying to click on the properties of the Arduino. I think I get it from here. Under the properties, there's a 3D model tab. And then in this 3D model tab, you just add something to it. So you can pick a file to add. That file can be an actual 3D model that you did in AutoCAD. There's also a library of 3D models that you can select from and drop parts in. So it's actually pretty nice and easy to learn how to use. But again, for the sake of time, I'm not gonna go through that today.
Before we move on from
Yes.
Component placement, do you have any
Sure.
tips for doing component placement for somebody getting started? Like, okay, what's your general rules of thumb in terms of placing components, especially for like doing a design for test? How do you make it easier on yourself while you're using the board?
Okay, so it's a very complicated question was asked. Is how do you know how to place components for design for test was one thing. What else did you ask, Sam?
Just rules of thumb.
Okay. So again, this placement stuff is an art form. What do you want to do if you have a high-speed trace? You want to make it as short as possible. Okay. So you got to think about what part of your circuit is operating at high frequency. How do I place the components that need to operate at a high frequency close to each other? That's one thing. You do that. Another thing is there any device that's a high current device? If there is, I don't want to have a long route or a thin route going between components, so I would place those components together. Where is the power supply? So somewhere the power is going to come into the board. I have to position the components on the board relative to where that power is. Like let's say one chip needs 3.3 and the power's over here. Another chip needs 5.5 and the power's over here. You would place them near the power domain that they would work on if you were able to. So, and what it really goes back to is understanding the schematic. So Like, so for example, I knew that I wanted this header pin to be right next to the Arduino because I just wanted to use it to probe the signals or to be able to open and close them, right? So I just knew as a designer that's where I wanted to be. Over here, we actually have a circuit that's doing something. This is a photodiode receiver. It's actually a transimpedance amplifier configuration. So as a designer, this, you would design the schematic in such a way that it's readable. But when you're doing the placement of those components, you're going to localize them so that they stay together on the board, right? So I would, for example, find this op amp, which is down here, and I'll just kind of put it somewhere. And I would go and say, oh, I know that I have this feedback cap and this resistor. They need to be close to that guy. So click on the cap. Here it is. I found it because of the nice feature of KaiKai that it highlights things for you. And then just move it over here close to that op amp. Okay? I don't know, Sam, do you think that helps? Are there any tips that you would provide?
So I guess all of that is great, and that's exactly what I would do in terms of making initial component placement, finding all your parts, getting them close together. I think one of the things that I've found, having done some PCB designs, is actually paying attention to your silkscreen before you send your board off, because by the time you get your board back, you're never going to remember what exactly is what. And having good silkscreen notes makes your assembly a lot easier. It makes, if you have problems with the board, it's like, okay, cross-referencing between the schematic and the board, it becomes a lot easier if you know what each component is. Things like that. So, and just don't be afraid to when you're doing the layout, just try different arrangements of the components to see, oh, this capacitor actually nestles nicely with the pads on my voltage regulator. Let's just put it there so that the leads are real straight, and you just try different configurations until things sort of fit together nicely.
Yeah, I mean, I think that's a great explanation. It's a highly iterative process, and I said this is where you put most of your time, is getting the components placed correctly so that your routes are optimized. Go for it.
So I'm going to sort of get an impression that I know the answer to this question, but for a board like this, it's pretty easy to sit down and lay all the components out and like do it in a day. But when you start working on stuff that's like bigger, I guess in my experience, it can kind of get overwhelming when you have like 100 components on your board and you're just looking at it the first time you import everything.
Yep.
What's your process when you have those like bigger, more complex boards for getting them faster to start maybe on where stuff should go?
Yeah, so the question from the audience was related to, this board that you're showing today as an example is relatively simple. You could probably knock it out in a day. That is absolutely correct, you could. But then when you add complexity, larger board, components that have a lot more pins, the way you get past that is on the schematic side. Like you have to think about the schematic more before you hop into the board domain, right? So let's say you had an FPGA that had 1,000 pins, and you've got to connect to a DDR3 or 4 that has 500 pins. Picking which pin goes where could save you hours, right? I mean, so it's really thinking about the schematic. Then, I mean, you'll have to iterate, right? You'll place the components, and you realize this is a bad, I shouldn't have done it this way. Like, it's hard to get it right the first time. And the biggest thing is, try, design reviews. Like, have other people look at what you're doing. Like, what happens when you're doing a design, you have tunnel vision, right? You're just sitting there, you're the only person, you think you're doing the right thing, but you could be doing something completely crazy. That if you have other people look at what you're doing, provide comments, that's a way to sort of speed things along, I think.
Do you tend to kind of just live in your EDA software when you're doing that, or do you like sit down with like a piece of paper and you're like, I want to think about it and then move in there? Do you just kind of like do it all in the schematic?
I mean, so the question was, do you do all of the design in the EDA software It's kind of a hard question to answer, right? So let's say you were doing an FPGA board. A ton of that design is actually the FPGA design itself. What pins can I connect to on this socket? And you have to have that sort of done before you can actually move it into the board, right? So a PCB designer is not just living in this. They're thinking about other things. Like you have to design the circuit itself. So at that point, I have this op amp, this transimpedance amplifier. I sat down and did some equations to check the gain and so forth. You don't do that in the EDA tool. But in terms, if your question is more like when you have a complex board, are you only doing it in the EDA tool? No. Like there are other things involved, right? Okay.
I'll add a little bit to that. So just like breaking down a complex design, I would probably break it into smaller components. Like that you're going to have your like voltage regulation section. Mm-hmm. So I'll just start by I'll wire up all the voltage regulator, like all the components that connect to the voltage regulators, all the local decaps for the voltage regulator, all like the local feedback for that. That'll be done, and then you can kind of have that off to the side already routed, and then you can move on to like, oh, I have all my input buffering. I'll do all the routing for that input buffering, all the feedback and all that stuff. And then what you do at the end is you sort of like take those blocks, move them around on the board, and then hook them all up finally. And you have to kind of like know when to like start hooking other things up too, because then you have your like longer signal routes because you need those to be clean. So there's like a lot of like interconnecting puzzle pieces together. But in general, if you know that some sections are like self-isolated, you can start by laying out those sections first, and that'll like reduce your components immensely. And then like a lot of your components end up being like decaps. So what you can do is you can say, oh, I'm just going to move my decaps around where I need them on like my FPGAs, like doing the decoupling on the power pins, because you know that you need those close to your power pins. And that like removes a bunch of components right off the bat.
Yeah, Sam, I think that's great. I mean, you can break it down into blocks, right? Like so. Thanks, Sam. That's a great help. All right. So we're at the stage that I wanted to talk about DRC. So we touched on this last time, that if you're going to design this board and you want to send it off to get manufactured, you have to meet DRC rules. DRC stands for Design Rule Checks. So the manufacturer will tell you, as we talked about last time, what the minimum space and trace are, what the minimum via size are, what the stack up of the board is, and so forth, right? So the KiCad has a tool that will check things for you, okay? Well, before you can do that, you actually have to tell KiCad what the rules are, okay? So where is that located? It's in File, Board Setup. And here on the left-hand side, so you can see in this part of the menu, it's talking about the layers that we've been operating on. So for example, the one I highlighted, which is the board outline, is called edge cuts. And you can see they tell you on the right-hand side what they think it's called, which is board contour. I don't know what that means, but to me, it's the board outline. But then down here is the design rule section. And the first thing you see is constraints. And the first thing you see in the constraints that we talked about is the minimum clearance, okay? So we talked about this board from Advanced Circuits. That's a $33 special, but you got to buy 3. It's actually $100. But the minimum clearance on that board was 6 mils. And that's the board that I actually built that I showed a picture of. So I entered 6 mils in here. The minimum track width was 6 in that spec. That's what I entered here as well. So as a designer, before you do anything really, you should go into the board setup and set up the constraints to match what your vendor tells you for the board that you're going to fab, okay? So that's, as I said, it's in this board setup menu. Another thing which is nice about KiCad, is that it has these things, this menu for predefined sizes. And it holds predefined sizes for tracks. So tracks in KiCad are traces and vias. So vias, we talked about what vias are. But you can do predefined sizes that after you're done with this and you're actively doing a design, it populates into this drop-down menu that you can just pick whatever track size you want. So it's convenient. Like I know I want a 6 mil trace, a 10 mil trace, a 50 mil trace, and so forth. I can just hop very quickly and do that. And that's the same thing with vias. There's a drop down here that I can pick which via that I want. All right. So now I'm just going to place some routes, this is the part of the PCB design where you're connecting one place to another on the board. So as we did before when we did the board outline, we selected the layer. I'm going to draw a trace on the top copper, which is known here as the front copper. So I've highlighted that. And then I pick the route track button right there. And I'll pick, let's say, 50 mil thick trace. Why not? And just make one. Uh-oh, what's wrong? What you can see is that KiCad is pretty smart. It's preventing me from making a connection to that place. So it knows what the net list is. It knows what is supposed to be connected to what, and it helps you. Let's try to do another one. Let's do this guy. So I picked the smaller one so that I could fit through. And you can see KiCad just sort of helps me. I don't have to click anything. All I'm doing is I started the route and go close to the place, and it knows where the connection is, and all I have to do is click, and it's done. So it's pretty straightforward. I can just pick another size, do another route, like that. If I don't like how my trace looks, I can do, I think it's Shift-D, which is a drag. I can kind of drag where that trace is, left or right. And then you can see that KiCad actually knows about the 6 mil space. So you can see as I drag that trace to the right, it's preventing me from dragging that trace into the hole on the right that it doesn't want to short out, and it's keeping a 6 mil distance. So that's a nice feature that KiCad will do for you. Okay, so I've routed on the top. Let's route on the bottom, but let's actually use a via now. So let's start a trace from this guy here. Oops. Start this guy. And let's say for some reason I wanted to go to the back side. Simply left click, then right click, place via. There's a hotkey for that. I think it's V. But then it places the via. What you need to do then is switch to the back metal, and it will route on the back side like that. I think there's a way to keep routing on the fly. So let's say we're on the back side and we want to go to the top side. Do you know what the shortcut is to keep routing after you put a via? Anybody?
I think if you use the hotkey, it'll continue.
Let's try it. So let's do the hotkey. So I'm holding the via. It did. Thanks, Sam. That's great. Okay. So we did placement. We did routing. Let's run DRC now. Do we have any questions at this point? Go for it.
Can you get back to how to start up the trace?
Sure. So starting up the trace. So first, sorry that I'm coughing, but you have to have a net. Do you have a net in your case? Like, do you have a definition, like a rat's nest? Okay, so if you don't have a rat's nest, I don't know that you can actually arbitrarily put a trace. So you have to have a connection in the schematic. Anybody else?
You can go in and change the net of a trace, can't you? So if you just place one in your PCB design, you can then connect it to the net that you want to connect it to, can't you?
Sure. You have to update the schematic. So yeah, as long as you update the schematic and then update the board, the net would be there. Okay. I mean, so we're actually getting close to the conclusion. Any other questions? Go for it.
If you have a 4-layer board with a route plane and
Yes.
how would it work for VIA on the front and the back board? Like, does it go through it?
Oh yeah. So in a standard PCB, a via goes all the way from the top to the bottom, drills a hole through the board. Yep.
Question would be, in terms of like auto traces, like how well does that work?
I don't know if KiCad has an auto routing feature, but Altium does certainly, and Allegro by Cadence has auto routing features. I don't know that KiCad does auto routing. I've never used it. So I think you actually brought up a great point that I would like to discuss, is that if we go back to the board setup menu and we click on physical stack up, this is actually where you define the layer stack of the board itself, okay? So at the very top, you can see that this is a 2-layer board. You can simply click that button and pick a larger number of layers, and that will update the appearance stack on the right. You can actually define thicknesses, define dielectrics, and use this to make a model that you could then use for RF simulation. Okay. So this is kind of all I was going to show. Now we're going to switch over to how do you make files that the printed circuit board house can use to do the fab. So before I leave this section, anything else? Okay. All right. So what are we going to do before we generate the files that we're going to send to the foundry? We're going to run DRC. We're going to check the design rules and see if this board is done in such a way that the foundry can fabricate it. Okay? So somewhere, here's the design rule check menu. I just clicked on it. And I'm going to run DRC. And what you see is that I have a ton of errors and a ton of warnings. Should I be worried? Who thinks I should be worried? I should be very worried because this board is not done at all. It's a total mess. So I should have a lot of DRC errors, okay? But I don't really care because I'm not actually going to fabricate this. But you can see it tells you things, okay? Warning, track has unconnected end. That could be a problem. What if you thought you made a connection but you actually didn't? The DRC will tell you, which is nice. If you double click the error, let's see. I think it will highlight. It may be, again, another thing that's nice about KiCad is if you have 2 monitors, the schematic here, the layout here, I mean, it just makes it so much more efficient. I'm sure we all do things that way anyway. Oops, I lost my menu. Yeah, I'm not sure how to get this to zoom, but I don't know. Yeah, that's it, Sam, you're right. If you zoom in like this, it'll hop to it. Yeah, you're right. Thank you. There we go. So if you zoom in really far, it's worried about A1D7. So you can see it here. It's pointing to this thing, and it's saying this guy has an unconnected end. I don't know why it's saying that, but maybe it's the way we did this via connection. So if I move this guy, you see it's actually not connected. In real life, it actually is, but it knows that KiCad did not make a snap between this trace on the bottom and that via. So I'm just going to go ahead and fix that. So if I fix that and rerun the DRC, that should go away. Maybe not. Maybe it's on the top side. try again. Uh-oh. Help me. Why? Why is this happening? Maybe we can move the via.
I would just delete the
Delete the via and do it again? Okay, let's try Sam approach. Let's do this. Let's do this. Let's do this guy. And then your secret was to hit V, right? So let's go over here. Let's go over here. This looks terrible.
Yeah,
But
it'll
that's
probably
okay.
be mad about that little jog, but
Uh-oh. Ah, track has unconnected in. Yes, it does. It's going nowhere. So we're going to get rid of this guy. Run it again. And finally, we killed this bug. But like as a PCB designer, you're going to want to be running this DRC regularly as you do the design, so you don't get at the end and you have a million errors that you have to fix, or you did something dumb 1,000 times that you have to go back and redo. Okay, so DRC, you should get yourself very familiar with it. Use it early on in the process, and read through every error. So some of these errors you may not care. For example, warning, silkscreen clip by solder mask. Well, what is that showing here? We have silkscreen that Sam talked about. It's something that's printed on the board that can tell the person that's soldering the board what's happening there. That silkscreen is actually going over the top of the copper here. So you're printing silkscreen on top of exposed copper. That's probably bad. So you probably want to fix that. Okay, so that's the discussion about DRC. Do we have any questions about DRC? No questions. Pay attention to DRC. Sure.
Just, if you did something like this, would it print the silk screen onto the bare copper, or would it automatically cut off the silk screen so that the bare copper isn't affected?
Yeah, so the question from the audience was, what actually would happen in this case? So if you sent the board for fab and you left this error, what would happen? So the board house may tell you you can't do this. This is going to be a problem. Or they may just print it over top, and you'll get it back. There'll be solder silkscreen printed on top of the copper. So depends on the board house. Depends on what you paid for. Just don't do it, I would recommend.
yeah, I think what I've usually seen is usually the board house will give you a preview, and I think they usually pull off the silk screen if you have exposed copper.
Okay.
I think that's what Osh Park does at least.
Okay.
But yeah, it can make it. You'll lose the silk screen. I recommend looking at the 3D viewer to fix all your silk screen errors. That's a good way to do it, in my opinion. I advised not to do it. Yeah, it's generally bad practice.
Yeah. So these kind of errors, I'm going to talk a little bit about how you can avoid them when we go to the generating the fabrication outputs. But anyway, that's DRC. So it's very important. You should do it early, do it often, and it will save you a lot of headaches. The other thing is inputting the constraints from the beginning. Don't screw that up. So if you put the wrong via size in, you put 1,000 vias and they're all wrong, you send it to the board house, they say, oh, your via is too small. You have to make all your vias bigger. You could have to completely redo the entire board. So the entry of the constraints is critical, and then checking the DRC is also critical. Okay. All right, so I kind of touched on this earlier about having multiple people look at your board, look at your design, doing design reviews. So the KiCad editor itself, as we were going through this process, you could see all of these layers that we were clicking that weren't real. So for example, the sheet boundary, it is not real. Like the board house is not going to put a sheet boundary on the board, even if you send it to them, for example. So when you're viewing the design here in the PCB editor, you have to be very careful, because these are not, what you see here is not what's actually going to get made at the PCB fabrication house. What's going to get made is generated from the Gerber files that this makes, okay? So I'm going to go through and show you how to generate Gerbers. That's pretty simple. You go to File, Fabrication Outputs, Gerbers, okay? And inside of here, you can pick which layers you want to generate. Well, I know that I want top and bottom copper, because if I didn't generate the top copper, it's not going to exist. I want the silk screen that we've just been talking about. I want the silk screen on the top. I want the silk screen on the bottom. I want the solder mask also. I want the board outline, okay? So that's just an example that if I were to make this board, I would need these files, and I'm going to generate them to send to the company that's going to fabricate. So all you do is pick the ones you want and plot, and it will generate a set of files. Alongside the Gerber files for each of these layers that we just talked about, you also need to make what's called a drill file. So the drill file is what tells the PCB manufacturer where to put the holes in the board. So they're going to do all the copper stuff, all the silk screen, all the solder mask, but they also have to drill the holes to make the vias and to have the places where the components will get inserted. So again, I'm not going to dive into the format of drill files, but there are a lot of options. The default that KiCad gives you is fine. I've never run into an issue with it that I can recall. So you just generate the drill file, and quickly it's done. So we have now, let's say we were done with our board. We generated the outputs that are going to get sent to the foundry. What do we do next? We do a design review on the Gerbers. Okay, so we're gonna look closely at those Gerbers and see if they are what we actually want to fabricate. Okay, typically you would do a design review here first, right? But we didn't complete the design, and there's really nothing to review. Okay, but I just want to point out the Gerber review because this is something that people may not think of. Okay, so we talked about it last week. KiCad very conveniently has a built-in Gerber viewer, which is a nice feature. Not all PCB software has this built in, but KiCad does. So you simply click the Gerber viewer from the project manager and File, Open Gerber plot file, and there's a folder where those files were generated. And we're just going to go in here and pick all of them. Say OK. The next thing we're going to do is bring in the drill file so that we can look at that. File, where is this guy? Open Exelon drill file. This is the guy we just made. I'm going to open that guy. OK, so now you can see those are the holes, right? If we were nerdy about it, we could open the file. These are human readable. The drill file certainly is human readable, but you can see that it's giving the type of drill. I heard like a mechanical engineer say something. Did I? G-code somebody? No? Yeah. So this is human readable G-code. And if you wanted to look at this, you could. If you wanted to write a Python script to do something cute, you could do that too. Okay. So why is this so important? Well, can you see actually here what the size of that hole is? Maybe. I don't know. I just don't trust it. But the drill file I do trust. I can find that via. And I can see that my drill T1 is defined as 15.7 mils. So I know that guy is going to be right. So I can actually dive in and check the correctness of this. What I can also do in the Gerber viewer is check this with a measurement. So I believe there's a measurement tool here, measure tool. I can just go like this and see if it's the desired size, which is very powerful. All right, so let's actually turn off layers, okay? And let's look at the top copper by itself. What am I, and let's put the board outline as well. But this is what the top of the PCB looks like. You can see that this looks much different than what you see in this view. It looks not. I mean, yes, you can sort of. The things are in the same place, but just the appearance is a lot more abstract here than it is in the Gerber viewer, where all you actually see is the pattern that's going to be in the top copper, and you need to actually do a really close visual inspection of this, searching for errors. Okay. We had that discussion about silkscreen, for example. So let's fire the silkscreen on here. Well, take a look. Like, the silkscreen looks like crap. We have these parts where the silkscreen is overlapping everywhere. Yes, you can. It's obvious here. You can see it. But there may be cases where it's hard to see in this view that the Gerber viewer makes it easier. But if you sent this to the fab, they're going to try to print Ohio State University across that copper, which is bad. So that's why you should take a look at the files before you send them off to fab. That concludes the meeting. So does anybody have any questions at all? I'm ready. Go for it.
When you're making boards for personal projects, are you a big silk screen art, like circuit board art guy, or do you tend to just put the minimum that you need for function in it? I know professionally that question doesn't make sense. Like, you're making stuff for fun.
Personally,
Yeah.
I never use silkscreen in my entire life, ever. But if you get it for free, I would do it. Like, I don't like pretty schematics. I don't like silkscreen. That's my own personal thing. It's probably a mistake too. Okay. Conformal coding. The question was about conformal coding. What would you like to know?
Just when you use it in general?
Sure. So conformal coding is a material that is used to block atmospheric contaminants from the components on the board. So let's say you had a board that was going to be in a wind turbine that is not hermetically sealed, but is going to be exposed perhaps to humidity, to the elements, and so forth. Conformal coating is just a material that covers it. It's like a, sealant. Does that help? And there are many, many kinds. Like, it's a whole chemical mess. They're often used for high voltage as well. So you can get a conformal coating that will increase the voltage rating. So, Trevor, please go ahead.
What about underfill?
The question from the audience was underfill. I don't know what that is. What is underfill, Trevor?
Sometimes you get a really good part, like say like an FPGA guy.
Oh, I do. Okay, so right. So yes, I do know what underfill is, and thank you for jarring my memory. So typically, underfill is a material that you would put underneath a ball grid array type package, which we didn't really talk about, but a ball grid array, it has some mechanical, they're not always mechanically strong. So if you twist the board, you could pop a ball grid array off. So underfill is used as kind of a strengthening technique for ball grid array packages. It's also used as to do hermetic sealing. So it can be used to keep contaminants from going under. If you accidentally spilled your Coke on your laptop, the underfill would keep that from going under the chip. John?
Yeah, are these layers that you're talking about, the hermetic seal and the underfill,
Are those just additional layers that you would draw on your PCB in the fabric?
Okay, so the question was these materials we're talking about, the underfill, the conformal coating, are they actually something in the PCB design process, or is it something that the PCB house does during the fabrication of the board? The answer is no. So this is something that you would go to an assembly house, and they would have a machine. It could even be like a spray paint. Like I've seen guys pot boards, and they just are, it's like you're painting a car kind of thing. So you're holding the board, you're painting it. The underfill is a dispensation thing where you have a syringe and you use surface tension for the underfill to wick inside. So I mean, it just depends. I mean, it's an after PCB thing, an additive process. Anybody else? Sure.
Could you maybe, I don't know if this will take too long, but like show us how to add another layer to that?
Sure, let's try. Yeah, let's do it. So you asked to add a layer and make a ground plane. Let's see if we can do it together. We have experts in the room. Okay, Flip is here. Gary is here, I think. There's Gary, he's back there. So I think you would go to board setup. You would make it, let's say, 4-layer board. And I think it's that easy. If I say OK, it's going to think. Now, you see on the right, I have N1, N2. So those are the inner copper layers. Okay? So that was easy. Let's draw a ground plane. We'll just click on this guy. I think, who wants to save me time and tell me what to do, Gary?
Right side.
Yep.
Add filled
Filled
zone. It's right underneath the
zone right here. So I click on Add Filled Zone
draw shape.
and just draw. So here's the beautiful thing. We asked, the audience asked for a ground plane, so that's what we're going to add. You can see when you start drawing the plane, it asks you what net you would like to assign to the plane. In this case, we're going to pick ground because that's what the audience member requested. And there are several parameters on the ground plane that you can specify. Remember how we talked about, where is this guy? These thermal reliefs. Yeah, you see here, pad connection, thermal relief. You can turn that off if you want, but we'll keep it. And let's just say OK. I think I want a rectangle. Is that hard to do, Gary, or no? Oh, son of a gun. So what I'm going to do is make the grid. I'm going to stop this immediately. I'm going to make the grid coarse to make it easy to plug things in. I'm going to go back. I'm going to do it again, like this. Pick ground. Say OK. And you got to draw it here, like this, like this. OK, and now we have a ground plane. V?
Letter B. B as in boy.
B as in boy. What does B do, Gary? Updates the board. So now, look at this. This is a connection point to ground, and it has made the thermal that we talked about earlier. It's that easy when you have a friend in the back that knows what they're doing. So, any other questions?
I'll just note one thing. I think for the stack up, you do want to shift around some of the layers
Let's take a look.
potentially, because that's more important if you're doing RF stuff. Because if you're doing like controlled impedance stuff, I know there's some tools with the controlled impedance you want that set up. You want the layers relative to each other set up as the actual stack up is, because that'll let the tool be able to calculate what your impedance is on the fly, which makes things nice.
Yep. Yeah, so thank you, Sam. Yes, you should actually use the tool to the fullest. So, okay. Anybody else?
Since we're talking about ground and power planes, how do you decide where to place a ground or a power plane within a board? especially when it gets to up to 40 layers, is there a specific way you decide where to place it?
Yeah, so the question was, how do you, let's say you had a 40-layer board and you had power planes, ground planes, how do you decide where to place them? So it's complicated. So you might not want a ground plane that covers the whole board, because you might have a noisy ground over here and a clean ground over here that you want to keep separated. So you'd have a dirty ground and a clean ground, analog ground, digital ground. So you might segment it like that. Power is the same thing. Maybe if you had a dirty power supply and a clean power supply, you wouldn't want to have planes next to each other, because then they could couple noise to each other. So there's a lot of, I don't have every answer, but it's not a trivial exercise. So the ground and power planning, if you have more than one ground domain, if you have more than one power domain, if you're trying to isolate noise, if you're, it can get very complicated. And it can make or break the design. John?
Is there a way, you touched briefly on simulations,
Yes.
KiCad stuff. Is there a way to easily export that list to load into simulation software from KiCad?
Yeah, so the question from the audience was, is it easy to take outputs from, or netlists from KiCad and import them into simulation tools? I don't have a lot of experience doing that, John. I know that KiCad does have a simulation capability now. I haven't really worked with it that much. So does anybody have knowledge of this that would like to comment?
So I know it's using ngSpice internally. I haven't actually ever used it, because I'm usually use a different piece of design software if I'm actually doing simulations. So I haven't really played with using KiCad to do the simulations, but I know that it's built in with ngSpice now, at least for doing analog simulations. I haven't ever exported netlists or anything like that. I usually just, because I'll usually just break it. What I did in the past before they added the simulation capability is just make a smaller version of the little thing that I want to actually simulate, and then throw that into, at that point I was just using LT-Spice or something like that. But I think if you're doing something like LT-Spice, I think KiCad's simulation environment is about reasonably good at that point. They might not have as many design libraries as like TI or as like Linear Technology has,
Yeah.
but I think it works. But I haven't ever used it.
Yeah. I mean, so thanks, Sam, for that. Like, one of the nice things about KiCad is all the files are actually human readable. Like, it's text. So the netlist is text. So if somebody must have written a converter from KiCad schematic to LT-Spice to H-Spice to I'm sure it's out there. I just don't have the experience.
I've tried to mess around with it a few times. The big roadblock that I run into is that I think you have to use Spice-specific symbols to actually get into like the Spice simulator in KiCad. Like, I can't just use whatever symbol I just loaded in or downloaded from like Ultra Librarian. I have to use the Spice symbol.
I see.
And then change it later. That might be different in 8. I was using 7.
Okay.
Maybe even 6 when I was doing all this stuff, but
Okay.
it seemed to be a little bit of a hassle at the time to like actually get Spice to flow well in KiCad.
Yeah, the comment from the audience was that they've actually tried it, and at the time they had to actually use different symbols for simulation than they did for the actual design. So it was kind of cumbersome, but that may be updated. We just don't know. So yeah. Okay. All right, guys. It's 8 o'clock. I'm done. Anybody else? One last one? Okay. Hey, thanks a lot for everybody listening. It was fun. I appreciate it. Take care.